So yeah, so we're starting unit 2, and unit 2 covers only one chapter, and that's chapter 7. Like I said, it's a lot of different applications of how to use definite integrals and what they are good for. All right. So 7.1 starts out with area applications. So the situation here is we have two curves. Think of two functions graphed out. And we want to find the area between those two curves. From one spot to the next. Meaning from one x value to the other. So here's the general idea. Let me actually just draw this. So the general idea is that I want to find the area between two different curves from an x value, we'll call it A, to an ending value, we'll call it B. Right? And I want to find this area here. Now we should know that we'll call the top one F and the bottom one G. All right, just so that so the top one is the function F, the bottom function is the function G, just so we have common language. So we want to find the area between F and G between these two values, whatever they happen to be. Well, hopefully we know that when you are integrating gives you the signed area. So if I integrate G, I would get the area between G and the x-axis. If we integrated F, we would get the area between F and the x-axis. Does that make sense? Now, if you look at the area underneath F, that's this area plus this area. Okay, so the area under F can be found by integrating the function f of x with respect to x from A to B, as long as f is a nice function, one that can be integrated. Similarly, the area under G can be found by integrating G from A to B. Does And if you think about this picture, the area between F and G is just the area under F, take away the area under G. So the area under F minus the area under G gives you the area between the two. And you can turn this into one integration if you want, because they have the same bounds and we're integrating both with respect to X. So since I have the same bounds, I'm integrating with respect to X, I can just take F of X minus G of X with respect to X to find the area between F and G. Now, there is a note here that we should understand. The way I drew it, the F was always on top, the G was always on bottom. So when F of X is greater than or equal to G of X, right? So F is the bigger one. F is the one that's on top. That'll give me a positive area. And that's the basics of it. That's the general idea. That the area under F minus the area under G gives us the area between F and G. And that's the general formula that I just had. If I want to find the area between two curves, F and G, where F is always above G on some interval, some closed interval, then I integrate along that closed interval. F of X minus G of X with respect to X. Okay. So let's take a look at this. We want to find the area between these two curves. Y equals X plus 4 and Y equals X squared minus 2 from X of -1 to X of +3. Now, the first thing I want to do is I want to ask myself, in that region between -1 and 3, which one of those curves is above the other? You can do this algebraically by plugging in values. Or more likely, you can either take your graphing calculator or some other graphing tool like Desmos and just graph them. So that's what I'm going to do. I'm going to take a look at Desmos. Y equals X plus 4 and Y equals X squared minus 2. Now, just so we're all aware, this is the graph of both. The line here is Y equals X plus 4. The parabola is X squared minus 2. there are times when the blue is above the red, and there are points in which the red is above the blue. But remember, our focus is from -1 to a +3. So we're looking in that region. Does that make sense? And in that region, the red is always above the blue. So the line is the one that's above the parabola in that region. Okay. This making sense? By the way, take off the. What we're really doing, in one sense, is finding this green area here. Okay, the area between this curve and this other curve, finding the total area in that case. From -1 up to 3, that's the area between those. By the way, as I didn't draw in my original picture a section of the graph going underneath the x-axis, but it's okay that my parabola goes underneath the x-axis. That's not going to hurt anything. Okay? That is perfectly fine. That portions go underneath the x-axis. It's always top curve minus bottom curve from one value to the next. All right, so now that we've established that, now we can set up the integration from -1 to 3. Like I said, the y equals x plus 4, that's on top. So that's like my f. And then x squared minus 2, that's on bottom. That's like my g. And we're integrating that whole thing with respect to x. Now you can, if you want, do this by hand. I'll do it once by hand. So if we were doing this by hand, I'd have -x squared plus x, 4 minus -2, that's +6, integrated with respect to x. That whole thing integrated with respect to x. I can go polynomial integration, -1/3 x to the third plus 1/2 x squared plus 6x from -1 to 3. We plug in 3. Subtract off whatever you get when you plug in a -1. On this first one, I got a 13.5. On the second one, I got -5 and a 6. If I'm typing that in my calculator, I get -31/6. So we get 13.5 minus a -31/6, which gives me 18 2/3, or roughly 18.67 when I round it to 2 decimal places. So if you wanted to, these you could all do by hand with the techniques that we just went over in chapter 5 and 6. Okay. However, that takes a lot of our time. So what I focus on mostly is just, can we set it up right? And then I'm just gonna put that entire thing into my calculator and integrate. And I know we've done this before, but I'll do it again. Do a definite integral with my calculator. So let me go and show that. There we go. So it's in the math menu, and then down to function integrate. I have the math print turned on, so it looks like an integration. Again, math, and then it looks like function integrate, FNINT. My bounds are from -1 to 3. And then you have to be pretty careful about how you type this in. X plus 4 minus, when you do your minus, x squared minus 2, make sure the entire x squared minus 2 is inside parentheses, because we have to distribute that negative sign, right? And then we're integrating with respect to x. Hit enter, and sure enough, you get the 18.67. Or 18 2/3 that we got earlier. If you have the classic version, then when you go to math, number 9 there, you have to put in your function first, and then you do a comma, and you say you're going to integrate with respect to x, and then you do a comma from -1, comma to 3. And you get the same thing, right? So no matter which way your calculator, which operating system you're running off of, we can save ourselves a lot of work if we are willing to use our calculator to do that definite integral. And that's what we'll do for the most part from here on out. And make life easy on ourselves. Does that work? So that's what we'll be doing. So I want you to try this one and utilize your calculator. I want you to make sure you set up the integration and then use your calculator to get the answer. And if you do get a decimal, you can just round it to a couple of decimal places. Call it good. All right. Now, in this case, between 0 and 2, the 1/2 x to the third plus 2 is the one that's on top. Okay? If you ever get into a spot where, let's say you don't have a graphing calculator to graph those two, again, you can graph those two on a graphing calculator if you want. Just see which one's above and which one's below in that region. If you didn't have that, then you could just plug in the lower and upper bounds and see, well, when you plug in 0, which one's above? Turns out this one is. When you plug in 2, which one's above? Turns out that one is. If you plug in things that are in between, like 1, again, that's above. So you could check this by plugging in various values. But when it's all said and done, 1/2 x to the third plus 2 is on top in that region. And x plus 1 is on bottom in that region. We're going to integrate with respect to x. We're integrating that whole function with respect to x from 0 to 2. And again, I just plug this into my calculator. And when I plug that into my calculator, I got approximately 1.33. So 1 1/3 or 4/3 if we were wanting an exacting.
I got 2.
Get 2.
I don't know what I did wrong.
I got 2 as well.
Oh, I got 2, huh? Oh, I misspoke. Yep, I typed mine in wrong. Oh, that's why. Yep, I got two too. Dang it. I had an exponent off. I put a square there instead of a cubed. Sorry. To get exactly two. Yeah, that was my mistake. My typing in wrong mistake. Hit the wrong thing when I typed it in. Now that, in certain ways, should kind of blow our mind a little bit. That it did come out to be two, because this is kind of a weird looking area. If we graph this, let's say we graph this on Desmos. We have y equals 1/2 x to the third plus 2. And then y equals x plus 1. And we're going from 0 to 2. So this is a really interesting shaped object. This green area here is where I'm looking at. And that green area, though, cubic is on top. The line is on bottom, but the area of that is just a whole number, which is 2. So that's pretty interesting in how that goes about. So yeah, very, very interesting that that weird shaped area comes out as a whole number. Okay. Now, these first two examples, I just gave the bounds of x was from -1 to 3 on the first one, or x was from 0 to 2 on the second one. One question we can ask is, well, what happens if the curves intersect? Can we find the area between their intersection points? So if the curves intersect, we find the area. Now, the phrasing that you're going to see is find the area of the bounded region between two curves. Bounded region means the enclosed region. So find the area of the bounded region between two curves. Now this one, I put f of x is equal to -x squared plus 4x plus 1. And g of x is equal to x plus 1. Just because we called one of them f and one of them g doesn't necessarily mean that the f is always going to be on top, right? We still have to graph it and see which one's on top. Okay. So let's go ahead and do that. Again, you could do this with your graphing calculator as well. I'm just doing it on Desmos because it's a little easier to project that way. So we have an f of x, which is negative x squared plus 4x plus 1. And then we have a y or g of x, which is x plus 1. And we're looking for the bounded region between these. Now, again, when I say bounded, that means completely enclosed. So if you look at where, let's say my cursor is over here, this goes up and to the left forever. So this is obviously not a bounded region. If you look at where this cursor is, this goes down and to the left forever. So that's not a bounded region. This is not a bounded region in here. This is not bounded. Again, not bounded. The only bounded region is the one in here. Everybody see that? And in that section, the quadratic is on top. And you'll notice that the point at which this crosses on the left-hand side is the point 0, 1. The point at which these cross on the right-hand side is the point 3, 4. So that means my x value is going to be between 0 and 3. Everybody get that? And that's the only bounded region. That's the only one that's completely enclosed. So now we know which one's on top, it's the quadratic. We know which one's on bottom, it's the line. And we know our bounds. Our bounds for the bounded region go from an x value of 0 to an x value of 3. Again, you can see that using graphing. You can also use algebraic techniques to do that as well. If you were going to use algebraic techniques to see where these cross, or let me restate that. If you wanted to find where these two intersect, which x values, all you have to do is set the equations equal to each other. So you just go negative x squared plus 4x plus 1 equals x plus 1. And then you solve. Okay. I like you, if I can see it on the graph, I tend to use the graph. that make sense? By the way, if you did this, you get negative x squared plus 3x equals 0. And then you factor out an x, you get negative x plus 3 times x equals 0. So either x is equal to 0, or this gives you x is equal to 3. That's how you get your two values. Okay. Graphically, the points of intersection on this one were 0, 1, and 3, 4. So we saw you'd have to go from 0 to 3. So if you want to find intersections algebraically, you can do that. Again, it takes a little bit more time, so I tend to do things graphically, tend to look at the graphs. And then once we have that, then we're ready to set up our integration. Integrate from 0 to 3. The one on top is negative x squared plus 4x plus 1. The one on bottom is x plus 1. We're integrating all of that with respect to x. And just like we did before, we'll type that into our calculator. Being conscious of the parentheses. And I got an area of 4.5. Barring me typing it incorrectly, obviously. So if you want to find intersections algebraically, you set, I should have said, you set the functions equal to each other. To each other. Find the intersections graphically, you just graph both and see what you get. Is that right? Again, bounded region means the one that's completely enclosed. I know I said this, but let me write it down on the board as well. The bounded region is the one that's enclosed and has a finite area. So it's the enclosed one with the finite area. I want you to try this one on your own. We have two functions here. f of x and g of x, we want to find the bounded region between those and then find the area of that bounded region between those. And again, I'm not saying just because one is labeled as F and one is labeled as G, doesn't necessarily mean that the F has to be on top in this particular case. It may be, it may not be, I don't know. So go ahead and try that on your own.
How do you type the square root in the Desmos?
Into Desmos, I believe it's SQRT.
Thank you.
All right, let me go through this if you haven't got it yet. So when you graph it, square root of x plus 3 does something like that. So that's my f, here's my g. And we get a bounded region that looks something like this. I didn't draw it really great, but hopefully, you know, I'll get the point. And the bounded region is this part. It starts at the point 0.3 and it ends at the point 4.5. So it's going from the point 0.3 all the way to 4.5. And that means when I integrate, my x bounds are going to be from 0 to 4. In that particular region, the f is on top. And the g is on bottom. Again, that's in that region. In the other regions, that's not the case. So my setup is going to be an integration from 0 to 4. Square root of x plus 3 minus the quantity 0.5x plus 3. All integrated with respect to x. And then something a little bit strange happens on my calculator. I want to show you what happens. But for right now, I want to just write it's 1.33. Rounded to 2 decimal places. All right, any questions about the setup and how that works? Area between two curves, area between the bounded region. Shoot. Okay. Now, this happened on my calculator, but it would probably happen on yours as well. When you integrate from 0 to 4, you get 1 point and then lots of 3's. And then at the very end here, we get 5, 4, 4. Now, that is a fairly strange phenomenon because we're dealing with powers of x, albeit a 1/2 power of x there. And we get something that starts out looking like 1 1/3 and then has that 5, 4, 4 on the end. It turns out if you would have done this integration by hand, you would have gotten exactly 1 1/3. But the calculator is thrown off by a little bit. So if you ask the calculator what fraction is this, it would not say 1 1/3. So if I said, what's the fraction that we just got? It'd say, can't turn it into a fraction. Such an ugly denominator. The reason why there's a discrepancy between what we would have gotten by hand and what our calculator is giving to us is how the calculator does integration. It does integration essentially by doing approximations and better approximations. Like when you first learn how to integrate, or what integration meant, you probably learned how to do some Riemann sums. That's kind of the process that the calculator is going through. Okay. And when the calculator gets close to a weird spot, it might get thrown off by a little bit. And the weird spot in this case is square root of 0. Because if you remember I'll just do this, square root of x plus 3. You'll notice that the square root of x plus 3 does not go to the left of 0, right? And so that kind of throws the calculator for a weird loop. And then when you get to the integration, it gets thrown off by a little bit. So hopefully, when we use our calculator, we know that, and we can say in our own heads, oh yeah, that's probably just 1 1/3, and the calculator messed up with its calculation somewhere because of the process it used. Is that okay? So that's all. Sometimes the calculator gets thrown off by a little bit. And that's especially true when you're close to asymptotes or when you're close to a thing that stops. That happens. All right, now let's take a look at another. We have g of x is equal to 4 over 2 minus x. Y equals 4 and x equals 0. This one's a little bit different. Than the ones we've done so far because we have we have 3 curves to look at rather than just 2. By the way, if there are multiple bounded regions that these 3 curves make up, we're going to pick the bounded region which has sides of all 3 curves. Does that make sense? So we're going to pick the bounded region which has sides of all 3 curves. Let's take a look at that. I'll use Desmos. Let's do this. What was the fraction? 4. Oh, 2 minus x over 2 minus x. So 4 over 2 minus x is one of the curves. Y equals 4 is another. And then x equals 0 is another. Okay. Now, do you see the bounded region? The bounded region is the one that looks a little triangular. It's not quite a triangle because it's not a straight line. But it's this region in here where the top is the y equals 4. The left-hand side is x equals 0. And the right-hand side is our rational function. Okay. We see all 3 points there. we have 3 points of intersection. One of them is 0, 4, the other is 1, 4. And the other is 0, 2. When we integrate, what is our x value going to and from? What's the left-hand most x value? 0, exactly. And the right-hand most x value is 1. So my bounds are going to be from x equals 0 to x equals 1. And you'll notice that the top curve of that region is the curve y equals 4. And the bottom curve is the g of x. Again, I'm talking about in that specific region. So we're looking at that bounded area. Top of that region is the y equals 4. Bottom of that region is the g of x, that rational function. And so now we're ready to do the setup and the integration. So the setup for the area, 0 to 1 of 4 minus my rational function, integrated obviously with respect to x. Be careful when you type this in. There's a lot of parentheses around. And in this one, I get approximately 1.23 as the area. So everybody else got? By the way, this one is something you could do by hand. Back in the well, you don't even need partial fractions to do it, but this is kind of akin to like an end game of partial fractions. We're integrating a constant number, and in this, when you integrate it, has the natural log of something, right? So just like in the partial fractions, you do the natural log of that. Then divide by the derivative. Yeah. So there you go. That's the idea. So your bounded region doesn't always have to just be bounded between 2 curves. It can be bounded between 3 curves. And if there are like multiple bounded regions, there weren't in this case. There was only the one bounded region. But if there are multiple bounded regions, pick the one that touches all 3 curves. Now, I want to talk at least once about a potential bad question. So make sure you write down. This is a bad question. And we'll state why in just a second. Let's say I wanted to find the area between f of x equals x minus 1 cubed and g of x equals just x minus 1. Now, first off, it's not even properly worded. You'd say from where to where. If it's area between there, from what x value to what x value. And you might say, well, it must be assuming it's the bounded region between those two, right? So even if it says find the area between the bounded region between those two, it's still a bad question. The reason that that's a bad question. Which one? F first. So I'll put the G up top and then the F. Oops. There you go. So even if it says bounded region, I want you to notice there's actually two regions that are bounded by those two curves. One of those has the f of x on top. The other has the g of x on top. Didn't do very well either. Second time either. That's fine. They are the same size though. So when it says find the area of the bounded region, it's ambiguous of what region. Are we asking for just one of the regions? Are we asking for the area of both bounded regions together? Or are we asking something where maybe this area counts as a positive area and this area counts as a negative area? Okay, there's a lot of applications where you count certain areas as positive and certain areas as negative. Does that make sense? So if we have multiple bounded regions that both touch, that they're both determined, I should say, by the two graphs, it's a little bit ambiguous about what the question is asking for when it says find a bounded region. So that's why that question is a bad question. All right? Because it could be interpreted in different ways. It could count one area as a positive and one area as a negative. It could count both the areas, both the bounded regions, as both being positive areas. Or you may be only looking for one of those specific regions, one of those areas. So if you ended up looking at a question like that, find the area between two functions or find the area of the bounded region determined by two functions, you'd want more information to be able to do it. We can find the area of, or we can find each of those areas separately, fairly easy, and then just determine what we want. Both those areas are counted as a positive, then we add them up. If one is counted as positive, one's negative, subtract them. If we only want one of the areas, then we only deal with the area that we want. And that happens anytime we have intersections. Anytime we have curves crossing at multiple places. We have more than just two intersections. Everybody okay with that? So be careful about that. Also, I know I didn't mention this in one of the previous examples, but here the F was on top, the G was on bottom. Remember that? What would have happened if you would have integrated with the wrong F and the wrong G? You flip-flopped.
Your answer would be negative?
Your answer would be negative, exactly. We wanted F minus G to give us positive areas. But if we do the bottom function minus the top function, all that does is negate everything we just did. So if you ever end up integrating and your answer is a negative, that may be an indication that you flip-flopped your F and G. You flip-flopped which one was on top, which one was on bottom. All right. All right, any questions about that? Pretty straightforward. Good. So that's what 7-1 is. 7-1 is always about finding the area between two curves or the bounded area that two or more curves make up. Now that we've looked at those areas, what we're going to do is we're going to move into 3 dimensions. And that's what 7.2 is about. 7.2 is about finding value of a 3-dimensional object using what's called the disk method. Now we're going to do a really specific value here. real specific object. So those areas that I was looking at, what I'm gonna do is I'm gonna take one of those areas and I'm gonna rotate it around some line. Most of the line, every line in 7.2 will either be a horizontal line or a vertical line. Okay. There are more advanced methods to rotate around different lines, but we don't do that. So we're gonna create a three-dimensional object by rotating an area around some line. And if you rotate it around a line, then you've made a figure in 3 dimensions. And so I'm gonna find the volume of that figure that I've made. Okay. Now I'm gonna show you what's going on. The disk method is essentially what happens if you cut cross sections in your area, just like normal integration. When you spin that cross section, those become disks. And then I'm going to take the limit as the width of the disks go to 0. That might not make a lot of sense right now, but I'll try to draw a picture of what is happening. And let's make it some area from A to B. So we're going to take this area. And let's just say I have a function which I'll call f of x. That's the top. And the bottom will be my x-axis, which is y equals 0. That won't always be the bottom. Let's say we want to rotate around the x-axis. So what I'm going to do is I'm going to take this area and I'm going to spin it around the x-axis. And what you're going to get is a three-dimensional object and I can't draw out from the board, but you can imagine spinning around out from the board. We're going to go all the way around the x-axis. So we're going to spin this around the x-axis. All right. So we get kind of a, how do I say? Almost like a cylinder, but we don't have a straight line at the end. Okay. Or like a filled in pipe of some sort. By the way, a lot of times when I spin this, what I'll do is I'll draw the image of my area on the other side. And this is not an official math thing, but I'll call this like the ghost image, all right? So It's like the image of my area if it were to exist on the other side. It's kind of handy sometimes to have that thing that, again, I call the ghost image, but of the area on the other side. And I'll show you why that's not for this particular scenario, but for some scenarios later, it'll be nice. So if you hear me refer to this as the ghost image, that's what, of my area. That's unique to me. Right? Now, think about what back in the day you would have done with Riemann sums to find the area. Well, back in the day, you took a bunch of rectangles, hopefully, back in Calc 1. And you'd fill up this entire space with rectangles. And then you let those rectangles get smaller and smaller and smaller, and that would give you the area. Okay? So I haven't rotated it yet. I'm just saying if I wanted to find the area of this green region, I'd take rectangles, make them smaller, and then that turned into the integration, right? Think about what would happen if one of those rectangles from the Riemann sum is spun around, in this case, the x-axis. What you would end up with is a three-dimensional disk. A fairly small disk. Now, the volume of the disk is pi times radius squared times the width of the disk. Think about what the radius of this disk is. If I'd spun this rectangle, the radius of this disk is really the height of this rectangle. And the height of this rectangle is determined by the function over here, in this case. And what's the width? Well, the width is just a very small change in x. And then we're going to take that as the limit goes to 0. So the radius is going to be determined by whatever function we have. We're going to call that r of x because it's going to be determined by a function. And sometimes it's just going to be f of x like it is here. Other times it'll be more involved. And then the width is a small change in x and we let the width go to 0 in the limits. And then we sum up all those disks. As the width goes to 0. Now, if we let the width go to 0 and we sum up all the disks as disks go to 0, that means the volume is going to be a summation of this when I apply the limit as all the disk widths go to 0. I'm still going to have a pi. My radius is now determined by some function. So this is radius squared. And the widths, as the widths go to 0, and I sum up, that's where this turns into an integration. Just like we did in the Riemann sum. So instead of getting a summation of lots and lots and lots of disks, it turns into an integration with respect to x. So the width was a change in x. And that change in x basically turned into my integration when I summed them all up and let the limit go to 0. That makes sense? Now, this is the value that we're going to use when we rotate around a horizontal line, like the x-axis. If you rotated this thing around a vertical line, then to create disks, all of your rectangles would have had to be laid flat. And then my rectangles have widths, which are small changes in y. So if we're going to rotate around like the y-axis, some vertical line, I need to do all my integration with respect to y. Leave a little bit of space here. And it's going to look the exact same. It's going to be some radius function, but now written with respect to y, squared, integrated with respect to y. And traditionally we use C and D because these have to be y values. And traditionally we use A's and B's for the x values. All right. So that's where these two formulas are coming from. They're coming from this general idea that we cut a bunch of cross sections, and when we rotate and sum up all the disks as the width goes to 0 or as the height goes to 0, if we're rotating around vertical, we get these two formulas. These are the same two formulas that I had on the board. If we have a horizontal axis of revolution, the volume using the disk method is going to be pi times the integration of radius squared with respect to x from A to B. If we have a vertical axis of revolution, then you do the exact same thing, but all with respect to y's as opposed to x's. All right. So let's find this value. So we're going to create a region, and that region is going to be bounded by y equals 4 minus x squared, x equals 0, and y equals 0 in the first quadrant. First quadrant just means upper right quadrant. And we're going to revolve that around the x-axis. And we'll find the volume of that object. Okay. Now, I'll draw this on Desmos and on the board as well. So y equals 4 minus x squared. X equals 0, y equals 0. And then it's in the first quadrant. So what we're looking at is this region here. First quadrant means I'm not looking at this one. I got that. That's second quadrant. This is the first quadrant. So I'm essentially looking between y values of 0 and 4 minus x squared for x above 0. Right? That's the region I'm looking at. We okay with that? Now let me highlight the points. There's 3 points there. 0 for the origin and 2, 0, where they intersect. I'm gonna draw some things. Now, we're supposed to revolve this around the x-axis. That is a horizontal revolution. Which means that if I were to draw one little rectangle in here, you'll notice that it's thin this way. In other words, the width is the change in x, right? So I'm looking at this region here. That region was created by a bunch of little rectangles. That might be able to see. This way. Take the limit as that, as the limit goes to 0. We're gonna revolve that around the x-axis. Again, I like to draw the ghost image each time, or what I call a ghost image. Again, that is not an official thing. And you can imagine we get this big disc, almost like a flying saucer shape. Okay. So this is a 3-dimensional object that goes out. Now I turn to my value formula. I know that the value right here is going to be pi a to b, some function that gives me my radius squared integrated with respect to x. I know that because it's horizontal axis of revolution. And also the widths of the rectangles I draw are all change in x's, right? Little change in x's. Pi is just the number pi. My x values on this region go from 0 to 2. Do you see that? So that's pretty straightforward. 0 to 2 are my bounds. Now here's where we have to worry about the radius. Radius goes from the top of our rectangle down to the bottom of our rectangle. The top of the rectangle is going to be different if I move this rectangle to the left and the right. But it's always going to be determined by this curve. So the top of the rectangle is always determined by y equals 4 minus x squared. The bottom of the rectangle since I am rotating around the x-axis always, it's always the x-axis. And the equation for the x-axis is y equals 0. Right? X-axis is y equals 0. So that means my radius is always from here to here. It's from 4 minus x squared down to 0. If you don't want to write that down to 0 when you type in your calculator, you don't have to, obviously. You can imagine why I'm writing it now, though. It's not always going to be 0. And then at this point, I just grab my calculator and type that in. Now I'm gonna do this two ways. I'm gonna integrate first and then leave off the pi, and then I'll plug in the pi. So, or you can do it the opposite way, doesn't matter. So we get this 4 minus x squared minus 0 quantity squared. On the inside, integrating with respect to x. If I times it by pi, it's about 53.62. That's the answer that Moodle's gonna probably ask you for. If you wanted the more exact answer, it's 17 and 1/15 times pi. Or 256 over 15 times pi. Is that okay? Moodle will probably ask you for the rounded version. Maybe. But if you were asked for an exact version, we don't. So that's the volume of this object that's been created through rotation. Any questions about that? And that's the essence of the disk method. You know what, I think what we'll do, instead of starting a new disk method today, I'll use this one, my example 2, as the starting point for next class period. All right, it's very, very similar to what we just did, so it'll be a good reminder without having to go over the same problem. Okay, so you have everything you need. If you wanted to do complete 7-1 homework, you can do that. 7-2 homework, obviously, we've just started on that, but we will finish that on Thursday. Okay, finish the material. All right, see you Thursday.